Welcome! In this differential equations tutorial, we are going to look at solving systems of differential equations using Laplace transforms. So if you're interested in that, stay tuned. So the first question I have is this system of differential equations. So what we're going to do is let uppercase u be the Laplace transform of lowercase u, and say it's a function of x, because here we see an x there. And so let's let v be equal to the Laplace transform of lowercase v of x. Okay, and so what we want to do here is take the Laplace transform of both sides of both equations. So let's begin. Laplace transform of u dash minus 2 times the Laplace transform of v is equal to the Laplace transform of 3. And then in our second equation, Laplace transform of v dash plus the Laplace transform of v minus the Laplace transform of u is equal to minus the Laplace transform of x squared. All right, so next, let's take each of these Laplace transforms. So for u dash, we then have s uppercase u minus u of 0, so that's minus 0. And then we have minus 2 uppercase u. No, it's uppercase v equals the Laplace transform of 3, but the Laplace transform of 3 is 3 over s, sorry. Okay, and so now let's go down to the second line. The Laplace transform of v dash is s v minus v of 0, so minus minus 1. Laplace transform of v is uppercase v, Laplace transform of u, uppercase u, and then over here we have x squared. So Laplace transform of x squared is 2 factorial over s to the power of 2 plus 1. Okay, so now we need to simplify this system, solve for the u and v, and then find the inverse Laplace transform of u and v. Okay, so let's tidy this up and do exactly that. So we have su minus 2v equals 3 over s in our first equation. In our second equation, let's put the minus u first. Then we have plus. Now s plus 1 times v is the part with the v next to it. Okay, now that's a plus 1. We want to take that over to the right-hand side by subtracting 1 from both sides. We have minus 1 minus 2 over s to the power of 3. Okay, so now we need to solve this system for u and for v. So to do that, let's multiply our second equation by s, so that we can make these u's vanish when we add the two equations. So I'm copying down the first one, and I'm multiplying the second one by s. We have minus 2 over s squared. Okay, great. So next we can add the two equations. We'll say adding. We have s squared plus s for the product of these two. I've just expanded that. And then minus 2 all in brackets times v is equal to 3 over s minus 2 over s squared. Okay, now here's the tricky part, is to write this in the correct way so that the Laplace transform is the inverse Laplace transform is easy to take. All right, so what do we want to do here? Probably factorize our left-hand side. Okay, so we need to factorize the left-hand side. We need to factorize the right-hand side. So for the left-hand side, we have s together with a 1, s together with a 2 times v. We need to decide the signs of these based on what we see here. One plus, the other minus, but the coefficient of the s is positive, so the larger of these two numbers we need to be positive and the smaller one negative. And on the right-hand side, we want everything to be over s squared. So if I multiply 3 over s top and bottom by s, I'll have that over s squared. So we have 3s when I do that. Now for the minus s, if I multiply top and bottom of that by s squared, then I get minus s cubed. And minus 2 over s squared is already over s squared, so minus 2. But we need to factorize this numerator here. So let's go to Mathematica to do that because it's a cubic and I don't want to muck around here. Okay, so I'll write factor. And then we are writing minus s cubed plus 3s minus 2. I'm pressing shift and enter. Okay, so we have our factorization there on the left or the right hand side. So it's minus in brackets s minus 1 squared times s plus 2, and that's all over s squared according to this. Okay, great. Now we can see that there are some common factors here, which will simplify what v is. So v equals minus s minus 1 squared times s plus 2 over s squared, s minus 1, s plus 2. And so now we can cancel the common s plus 2 and the common s minus 1. Okay, so let's go ahead and do that. Canceling the s plus 2's, canceling one of the s minus 1's. So that will give us a power of 1 up there. What we get then is v equals minus s plus 1 on the numerator, 1 minus s, and then that's over s squared, which we can also write as 1 over s squared minus 1 over s, which is easy enough to take the inverse Laplace transform of. Okay, so now that we have that, let's go back and find what u should be equal to. So if we just take, I don't know, do we want to take the first equation maybe? Let's take the first equation, s u is equal to 2v plus 3 over s. Okay, and so then this is, if I sub this in, we've got 2 over s squared minus 2 over s plus 3 over s, which is 2 over s squared plus 1 over s, and then we want to divide that by s so that we get u is equal to 2 over s cubed plus 1 over s squared for u. Okay, fantastic. So we have this, and we have this line up here. So now we want to take the inverse Laplace transform of these terms in here so we get lowercase v and lowercase u. Now remember that the Laplace transform of x to the power of n is n factorial over x over s to the power of n plus 1. So if we're inverse Laplace transforming this, let's divide both sides of this by 1 over n factorial, or n factorial that is. So n factorial Laplace transform of x to the n is 1 over s to the n plus 1. So what we see then is that taking the inverse Laplace transform of both sides of this, inverse Laplace transform of 1 over s to the n plus 1 is equal to 1 over n factorial x to the power of n. Okay, and so now we can take the Laplace transform of u and v. So let's go ahead and do that. So we have u equals 2 over s cubed plus 1 over s squared. And so inverse Laplace of uppercase u is lowercase u as a function of x. So we have 2 inverse Laplace of 1 over s cubed plus inverse Laplace of 1 over s squared. All right, now according to this, the inverse Laplace transform of 1 over s to the power of 3, here the n would be 2, so then we get 1 over 2 factorial x to the power of 2, and then over here we have the n would be 1, so we have 1 over 1 factorial x to the power of 1. And so this simplifies to give us plus x. Okay, so u of x is x squared plus x. All right, next, let's do the same thing for v. So inverse Laplace of uppercase v is lowercase v of x, which is inverse Laplace of 1 on s squared minus inverse Laplace of 1 over s. So the inverse Laplace of 1 over s squared is just x as we got there. And the inverse Laplace transform of 1 over s is just 1. So lowercase v of x is x minus 1. U of x is x squared plus x. Question 2. Okay, so in question 2, we've got to do the same thing. U minus 8 is the Laplace transform of u dash plus 5u, the Laplace transform of 5u. So this is uppercase, minus 12 uppercase v equals 0. Now for the second equation, s uppercase v minus v of 0 is 3 plus 2 uppercase u minus 5 uppercase v equals 0. Now be careful because 5 and s look a lot alike. Okay, so you want to write your 5 so it looks like a 5 and not an s. All right, so let's go ahead and continue this. So we need to collect like terms and factorize the coefficient times u, and similarly with the v. So s plus 5 times u minus 12v equals 8. All right, now for the second one, we have 2u plus s minus 5 times v is equal to 3. So now let's attempt to eliminate u by multiplying each equation so that the u's have the same coefficient and subtraction makes them vanish. So multiplying the second equation by s plus 5 and the first equation by 2, we have 2, thinking about s there, so 2 outside of s plus 5u minus 24v is 16. Now with the second equation, multiplying that by s plus 5, 2s plus 5 u. Now s plus 5 times s minus 5 is s squared minus 25, and that's times v. And then on the right hand side we have 3 brackets s plus 5. Okay, so now these two are the same, and subtraction would make those vanish. So let's take the second equation minus the first equation. And so when we do that, the u parts vanish, and so we will have plus 24v there, but we have a minus 24v. So what we get then is s squared minus 1 times v equals 3s plus 15. You see what I've done there? I've expanded that. And then we have minus 16, which incidentally gives us 3s minus 1. Okay, so dividing both sides of this equation by s squared minus 1, we get v equals 3s minus 1 over s squared minus 1. Now it looks like we should use partial fractions for this one. And so we want to factorize s squared minus 1 as s plus 1 times s minus 1, and then use partial fractions on the right-hand side where there's a fraction. So let's have a look at that. So we want to write this as a over s plus 1 plus b over s minus 1. Now, if we put this back together, it'll look a bit like this because the denominator will be s squared minus 1. So let's put this back together. So we have a times s plus 1. And we have plus b times, oh no, that wasn't s minus 1, wasn't it? Yeah. B times s plus 1. This is all over s squared minus 1. Okay, so rewriting this, what we're looking at then is solving for a and b such that a times s minus 1 plus b times s plus 1 is 3s minus 1. Now, there's a little trick to doing this. What we want to do here is say when s is equal to 1, and the reason why we choose that is because it makes this vanish, and it makes it very easy to see what b is. So when s equals 1, this vanishes here, and we have 2b, 1 plus 1 is 2, equals 3 times 1 is 3, minus 1 is 2, so b is equal to 1. And then similarly, when s is equal to minus 1, to make this vanish, but let's get another page. So when s equals minus 1, we get minus 2 here, so minus 2a is equal to minus 3 minus 1 is minus 4, and so a is equal to 2. Okay, so what this tells us then is that uppercase V can be expressed as 2 over s plus 1. Where was b? Plus 1 over s minus 1. And if you put this back together, you'll see you get 2s minus 2 plus s plus 1, which is 3s minus 1. So that works. All right, so now we can take this, sub it in where we have an expression for u. Okay, so let's say recall from above 2u plus s minus 5v is 3. So what we want to do is sub this in for the v, but I think we should probably use this form of it to do that. So 2u is equal to 3 minus s minus 5 times v, but v, let's sub in 3s minus 1 over s squared minus 1. Okay, and so we want this to be all over that denominator, s squared minus 1, on the right-hand side. So multiplying the 3 on top and bottom by s squared minus 1, we have 3s squared minus 3. And then we have to expand s minus 5 times 3s minus 1. And then that's all over s squared minus 1. And this, remember, is 2u. Okay, again, remember that we want to make this right-hand side, we want to put it in a way that looks like it's easy to take the inverse Laplace transform of. All right, so you got to do a little bit of work to do that. So let's continue on our expansion here. 3s squared minus 3, and then we have 3s times s is 3s squared, so with a minus, that's minus 3s squared. And then we have minus s, minus 15s is minus 16s, but there's a minus out here, so plus 16s. And then minus 5 times minus 1 is plus 5, but then there's a minus, so minus 5. All over s squared minus 1. All right, continuing. So we can see here that our minus 3s squared vanishes with the 3s squared. 16s minus 8. And then if we divide by 2, we have 2s squared minus 1 brackets in the denominator, and that is our uppercase u. Okay, so we can divide that 2 into the 16 and the 8 because they're both even. That's easy to do. So 8s minus 4 over s squared minus 1. And we want to use partial fractions on this again so that it's easy to take the inverse Laplace transform of it. Okay, so we know the factorization of s squared minus 1 is s plus 1 times s minus 1. So let's write then 8s minus 4 is equal to a times s minus 1 plus b times s plus 1. And we want to find our new a and b. I don't mean to say it's the same one as we used up for finding v. It's a different a and b here. Anyway, okay, so when s is equal to 1, this vanishes and we get 2b equals 8 minus 4. So b is 4 over 2, which is 2. And then when s is minus 1, this vanishes. We have minus 2a here, and we have minus 12 here. So minus 12 over minus 2 is 6. Okay, and so now we've got that this up here can be expressed as 6 over s plus 1 plus 2 over s minus 1. And so taking the inverse Laplace of each of these, inverse Laplace of 6 over s plus 1 gives us lowercase u as a function of x is 6e to the minus x plus 2e to the plus x. Okay, doing the same thing up here for v, lowercase v is 2e to the minus x. Remember, s minus minus 1 is s plus 1. And then we have e to the plus x. All right, so there's our lowercase v, and down here is our lowercase u. Question 3. Okay, in question 3, let's let uppercase y of s be the Laplace transform of lowercase y of x, and let's let uppercase z of s be the Laplace transform of lowercase z of x. Okay, so when we take the Laplace transform of the first equation, we get s uppercase y minus y of 0, which is 1, and then minus uppercase z equals 0. Now for the second equation, we have uppercase y minus s z. Now let's put a bracket around this to be careful. So sz minus that 1 for lowercase z of 0. Okay, so now that we have this, we need to simplify this and collect like terms, etc. So we get s y minus z is equal to 1. And then we have we have just single y minus s z. That's plus 1, but when we take that over to the right-hand side, we then get minus 1. Okay, so now we need to solve this system for y and for z. Now it looks like here I'll probably just multiply the second equation by s. So let's go ahead and multiply the second equation by s. So rewrite the first one. Okay, there we go. So continuing, we want to subtract one equation from another, so let's take first equation minus second equation, so we get rid of some minus signs there. Okay, so doing that, these terms with the y next to them, those will vanish. So we'll get s squared minus 1 times z equals 1 minus s, which is s plus 1. And so then dividing both sides by s squared minus 1, we have uppercase z is equal to s plus 1 over s squared minus 1. But s squared minus 1 is s plus 1 times s minus 1. And so we can cancel the common s plus 1, and then we'll get 1 over s minus 1 for uppercase z. All right, great. So what have we got so far? We have uppercase z is 1 over s minus 1. We want to get uppercase y. Now let's just take our second equation, which said y equals sz minus 1. So what I'm doing is I'm just looking at this line right here, taking this over to the right-hand side. So I get plus sz minus 1 is y. Good. So we want to then sub this in for that z. So we have s over s minus 1 minus 1. Now if I multiply top and bottom of this by s minus 1, then we get s over s minus 1 minus s minus 1 over s minus 1. So now we can put this over the same fraction bar called vinculum. So y equals s minus s for the numerator plus 1 all over s minus 1. And so we've got y equals 1 over s minus 1 because those two s's vanish there. All right, so uppercase y is the same thing as uppercase z. So let's take the inverse Laplace transform of both of those equations. So lowercase y of x is the inverse Laplace transform of uppercase y of s, which is the inverse Laplace transform of 1 over s minus 1. And so that is e to the power of plus 1x. So e to the power of x. Similarly, z of x is also e to the x. Okay, this seems a little bit too good to be true, so let's try this and say let's test or check. So y dash is e to the x, just differentiating e to the x. Okay, so y dash minus z is e to the x minus e to the x, which is 0. Now the second line says y minus z dash, so this is e to the x minus e to the x. This is also equal to 0. Okay, good. So it satisfies the two differential equations. Does it satisfy the initial conditions? So let's find out. Y of 0 is equal to e to the power of 0, which is 1. Yes, that checks out. Okay, and similarly, z of 0 is e to the 0, which is 1. So this all checks out just fine. Question 4. Okay, taking the Laplace transform of the first equation, we have s uppercase u minus 3 plus 4 uppercase u minus 6 uppercase v equals 0. Taking the Laplace transform of the second equation, we have s uppercase v minus 2 plus 3 uppercase u minus 5 uppercase v is 0. Okay, so now we want to collect like terms, solve these for each of u and v, and then apply the inverse Laplace transform to both of those equations. So let's do that. We have s plus 4 times u minus 6v equals 3. And then we have 3u plus s minus 5v equals 2. Okay, now let's just multiply the first equation by 3 and the second equation by s plus 4. So we've got then 3s plus 4 u minus 18v equals 3 times 3 is 9. And then in the second equation, we have 3s plus 4 u plus s plus 4 s minus 5 v equals 2 brackets s plus 4. All right, so now we want to subtract, say, equation 2 and subtract equation 1 from equation 2. That looks better to me. All right, so let's do that. Now, when we do that, these vanish. We want to expand this, and then we'll be subtracting minus 18, which is plus 18v. All right, so we have s squared for s times s. Then we have minus s. And then we have minus 20. But then plus 18 gives us minus 2. And that's all times v equals 2s plus 8 minus 9 is minus 1. All right, so let's factorize the left-hand side. S with a 1, s with a 2, minus and a minus. We want the bigger of the two of these to carry the minus sign. And then there's the v there. Okay, great. So next, let's solve for v by dividing by s plus 1, s minus 2. So we have 2 over s minus 1 over s plus 1, s minus 2. We want to use partial fractions on this and call this a over s plus 1 plus b over s minus 2. Now, putting this back together, we have a times s minus 2 plus b times s plus 1 should be equal to 2s minus 1. And so one way to do this would be to say when s is equal to 2, this term vanishes and we have 3b for this. 3b is equal to 2 times 2 is 4, 4 minus 1 is 3. So b is equal to 1. Okay, now let's make this term vanish and say when b is equal to minus 1, this vanishes, and so we have minus 3a is equal to minus 3, and so A is equal to 1. Okay, B is equal to 1 and A is equal to 1. So does this check out? S minus 2 plus S plus 1 is 2S minus 1. Okay, good. So then this says that V is equal to 1 over S plus 1 plus 1 over S minus 2. And we already know that this is 2S minus 1 over S plus 1, S plus S minus 2, sorry. Okay, because we now want to find U. So let's recall we had 3U plus S minus 5V equals 2, right, from this line. Okay, so solving this for uppercase U, we have 3U equals minus S minus 5V plus 2. So let's now sub in this version of V into there. We have minus brackets S minus 5, 2S minus 1, all over S plus 1, S minus 2, and then we have over here a plus 2. Okay, and so we need to expand this. We also need a common denominator of S plus 1, S minus 2. So then we have, let's see, 2S times S is 2S squared, so minus 2S squared. Then minus 10S minus another S is minus 11S, but there's a minus out there, so that's plus 11S. Minus 5 times minus 1 is 5, and then times minus 1 out here is minus 5. Okay, then we need to add to that 2 times S plus 1, S minus 2, so that that's all over S plus 1, S minus 2. Okay, continuing our expansion of the numerator. Now we can divide by 3 here as well and say U is equal to this over 3. Okay, expanding that numerator even more, we have minus 2S squared plus 11S minus 5, and then over here we have plus 2S squared. Then we have minus 2S plus S is minus 1S. Minus 1 times 2 is minus 2S. And then another minus 4. Okay, we're getting somewhere. Now we can see that these two terms can vanish. 11S minus 2S is 9S. So then we have U equals 9S minus 9 over 3 bracket S plus 1, S minus 2. Now we can take that 3 and cancel a 3 in the 9 in both of the 9s, but there's also an S minus 1. But I see that's not going to cancel because I don't have an S minus 1 down the bottom. Okay, so let's just write this as 3S minus 3 over S plus 1, S minus 2. Okay, great. Now we need to break this up using partial fractions. So let's call this P over S plus 1 plus Q over S minus 2 is that 3S minus 3 over S plus 1, S minus 2. Okay, so putting this back together, we have P times S minus 2 plus Q times S plus 1 should be equal to 3S minus 3. Now, when S is equal to 2, this term vanishes, and over here we have 3Q, and over here we have 3 times 2 is 6, minus 3 is 3. So q is equal to 1. Now when s is equal to minus 1, this term vanishes, and over here we have minus 3p. Over here we have minus 3 is minus 6. And so from that we get p is equal to 2. Okay, and so that tells us then that u is equal to 2 over s plus 1 plus 1 over s minus 2. So if you put that back together, you get 3s minus 3, matching what we have there. Okay, good. Now, let's collect what we've already learned about v. So we learned that v was 1 over s plus 1 plus 1 over s minus 2. Okay, now it's time to take the inverse Laplace transform of both of these. So lowercase u as a function of x is the inverse Laplace transform of uppercase U of s. And so that's 2 inverse Laplace of 1 over s plus 1 plus inverse Laplace of 1 over s minus 2. And so for this, we get 2 e to the minus x plus e to the 2x. And this is our u of x. Okay, now for the second equation there, lowercase v of x is inverse Laplace of uppercase V of s, which is inverse Laplace of 1 over s plus 1 plus inverse Laplace of 1 over s minus 2. And so that's e to the minus x plus e to the power of 2x, because we have a minus 2 there. Okay, and we have solved that system with these two solutions.